Hello and welcome. Today we're going to talk about containers, specifically Docker containers. Docker being the company that makes the container technology that we're interested in. Before we talk about what a container is, we're going to talk about what has led us to the point where containers are interesting and useful. And that requires us to go back in history a little bit and talk about computing and the kinds of computers that you can compute on in recent history. So back in the beginning, in the old days, there were bare metal machines. Bare metal machines is just a term we use for any physical device, preferably not melted, that allows you to do computing in a contemporary style. So this would be your laptop would be an example of a bare metal machine, a desktop computer that you actually put on or under your desk, a server computer, which is a box that has a computer in it that you could store in an office or at home or in a data center somewhere. It doesn't matter where. But these are physical devices. And on each of these physical devices, we install an operating system, be that Windows or Mac OS or Linux or Unix or some variation of any of those. We install an operating system on these physical computers. And that operating system allows us to then install applications and other software that let us do things that are useful to us with that machine. This is the level of computing that you're most familiar with, that everybody is most familiar with. Physical machines that come in boxes. And the advantages are obvious. You get a computer and you can control it. You can install whatever software you want on that computer as long as that software is compatible with your operating system. And you can also control the hardware to some degree. If you need more RAM, you can buy more RAM and put it in, as long as you can open up that box. If you need more storage space, you can buy an extra hard drive and plug that in. If you need a mouse, you can attach it. If you need a better monitor, you can hook it up, right? So with a bare metal machine, you have ultimate control over the hardware within the limits of what is possible with the machine that you have. And you have ultimate control over the software within the limits of whatever software is compatible with the operating system that you're running on that machine. The downsides of a bare metal machine compared to other ways of doing computing are that the boxes take up a good amount of space, especially the high power ones that have lots of storage space, lots of RAM, lots of graphics cards, and so on. They come in boxes. Boxes take up space. If you need 100 of these, that's a lot of boxes that you're going to stick in a room somewhere. Also, maintaining a computer like this is very time-consuming and resource-intensive. All the software needs to be upgraded every once in a while. The hardware also has to be kept up to date, replacing things as they go out of date. So maintaining, keeping it going, you can't just buy it and then let it run. You constantly have to do little tweaks to keep it working properly. Also, if you want to replicate the configuration of one machine and copy it to another, let's say you're testing the software that you're working on one machine and you want to make another test computer with the same setup that you can test it at the same time with, configuring and copying configurations can be complicated unless the machines are identical, which they often are not exactly identical. Often there are slightly different versions of things installed, so replicating the same configuration can be challenging, especially on different machines that are significantly different. Also, you have a finite ability to improve and scale up the hardware. There's only a certain amount of hardware you can plug in. And same with software, you have a finite amount of software that you can run at any moment because there's a limited finite amount of memory and processor power, storage space, and so on. The next evolution of computing would be what we call blade and rack servers. These are two slight variations on the same idea, where you have multiple computers that have been miniaturized, that have been made physically smaller on a single circuit board that you can slot into a single box. So whereas with the bare metal server you would have had, or the bare metal machine, you would have had one computer per box, here you can have 10 computers in the same box. So ultimately it's the same concept as a bare metal machine, it's just that you have more than one in the box. And certain aspects of these computers can be shared. So whereas with your bare metal machine you would have had a fan that's blowing and keeping your processor cool, here in this kind of a blade or rack server you might have a fan that is being shared among these 10 computers. There might be a power cable that in a bare metal machine would only be powering one computer, here the power cable can be plugged into that box that powers 10 computers. Blade and rack servers, those two terms are really differentiated by how much of that shared infrastructure is shared compared to how much is independent for each of these cards. But that distinction is not extremely important for us. The idea is you've got a box that has more than one computer plugged in. These are still hardware machines. Each one has its own operating system and software applications installed on it that's independent of the others. So much the same as a bare metal machine, just miniaturized to a certain degree with a little bit of shared resources. Sometimes they can even share the same network connection, for example. They have their own downsides, which is they get hot. You have 10 computers running in a box. That requires more cooling than your single bare metal machine. So you need more fans, maybe some air conditioning to keep them running. Similar to a bare metal machine, you have to maintain these, keep the hardware up to date, keep the software up to date. And that, of course, like we said, is resource intensive and potentially time consuming and expensive. And this leads us to the next evolution that improves upon some of these concepts. And this would be virtual machines. Virtual machines are, as they sound, virtual. They are not anymore, we're not talking about hardware. Of course, there has to be hardware. There has to be a physical computer. But the virtual machine is a virtual computer that runs on the physical computer. We call the physical computer the host machine, and the virtual machine can be called the guest machine, or just the virtual machine, we sometimes say. So the physical host machine has certain infrastructure. It has a physical device with RAM and hard drive and storage space, I guess it's hard drive, and processor power and graphics cards and all the other hardware parts of the circuit board that you're familiar with. But on that machine, in the world of software, we can emulate, we can create virtual versions of other computers. So on the host machine, we can run a virtual computer with its own operating system virtually. We can run another virtual computer with its own operating system that might be different from the first. And we can run a third virtual machine with its own operating system that, again, could be different from the other two. So on a single host machine, you can be running virtual emulated other machines in the software world. There is a management software that allows this to happen called a hypervisor. It's sort of a supervisor software that makes sure all the virtual machines that you launch on the host machine are running correctly and are sharing resources nicely with each other. So none of them hogs all the RAM of the host machine or hogs all the storage space of the host machine and so on. So this is a sort of supervising level of software that is included in this virtual machine technology. So ultimately, again, now you have the world of being able to run more than one computer, but these are virtual computers, and you can run many of them on a single physical device. So this is different from what we've seen before. The downsides of this are going to be that the fact that each one has its own operating system. As we'll see, this creates bloat. This means that any one of these virtual computers takes up a lot of hard drive space, uses a lot of RAM, requires lots of disk storage, processor power, and so on, because operating systems are big, bloated pieces of software typically. So the fact that each virtual machine has its own operating system means that each one takes up a large footprint. These are not easy to launch, fast to run virtual environments. These take a while to boot up, just like any operating system does, and then consume a large amount of RAM, processor power, and so on to run because of the fact that they each have their own operating system, and you might be running several of those operating systems at the same time on the same host machine. But the benefits over rack, blade, and bare metal servers are that it doesn't take as long to set up a new computer. You don't have to buy a physical device and install all the hardware you want. You can just launch some software, fiddle around with it, and create a virtual computer of the type that you're looking for. They also reduce the risk of you accidentally choosing the wrong stuff for your hardware machine. Because this is all virtual, you can stop and start, change configurations very easily. So you've simplified the process of setting up a computer of the type that you're looking for because it's all virtual, controlled by software. The downsides of a virtual machine are that you've got the operating system in there, which, as we said, is a large piece of software, usually very large, although there are small miniature operating systems with small footprints, which we'll talk about perhaps. But this allows a large amount of overhead, a large amount of power and resources are necessary to run these virtual machines. That means they're not very portable, not easy to move it from one machine to another, one physical host machine to another. It wouldn't be easy for you to take your virtual machine and transfer it to a new physical host machine because of the fact that the file size of that operating system is so large. All right, and in walks containers. Containers are the latest, greatest computing environments in this history of trying to pack more computing power into smaller and smaller spaces. Containers, like virtual machines, are virtual. They are software-controlled virtual environments. And here's a diagram of containers. In addition, next to a diagram of how virtual machines work. So virtual server is just a use of a virtual machine to make a server. So if you compare how a container looks in this diagram to how a virtual machine looks in this diagram, you'll see that they're very much the same. You've got a physical hardware, that's a physical computer that is ultimately going to be running all this software. That computer has an operating system installed on it. Whereas the virtual machine world had a supervising level of software called a hypervisor that made sure all the virtual machines were running nicely. The container technology includes what we call the container engine, which serves somewhat of a similar purpose, makes sure all the containers are acting nicely and behaving correctly as well. And then you have the actual virtual computing environment that's in this box here for a container that's similar to what we saw with a virtual machine. And you'll notice the difference is that the containing environment for a container, the computing environment that a container runs in, does not include the operating system. So whereas a virtual machine has this layer of the operating system for that virtual environment, the container does not. However, that doesn't mean you can't have an operating system that is running within the container. You can. And this is where container magic comes into play. The container allows you to have a specific operating system configured for the container, but the container doesn't need to encapsulate that entire operating system itself. It only needs the bare minimum stuff that is necessary for your app to function on the host machine. So it might be that there is none of the operating system included in the container, like this diagram suggests, and that means that if you configured, let's say, this container to run with a different operating system than the host machine, the container engine takes care of providing all the resources that that type of operating system would normally need without it being required to be inside the container itself. And so that's the magic of a container. The container engine allows a container to function as if the operating system was encapsulated in the container when in fact it's not. It's external. Right? That's the magic. And so that makes containers more attractive because you can now easily move a container from one physical machine to another because the file size is very small because the operating system is not included. You can run a container within a physical host machine, like we've been saying, but you can actually run a container within a virtual machine as well. So you could have, and this is actually a very common setup, you could have a physical host computer, the physical hardware computer that you have in front of you, running virtual computers, virtual machines, using virtual machine technology. And each VM, each virtual machine, could actually in turn be running several containers within that. So you can run containers on physical host devices, but you can also run containers within virtual host devices. So they are ultimately flexible. So this is great for situations where you need to boot up computers of new instances of computers at will, quickly, efficiently, in a portable fashion, move them from one server to another, move them from one computer to another, without worrying about what operating system is on the host machine or whether the host machine is even a physical machine or a virtual machine. You can move these things all around a network. Now, we said that a container does not have to include the operating system, but there's a caveat here, which is you can include an operating system in a container if you wanted to. And in some cases, it's hard to figure out what are the necessary dependencies for a given application or a given piece of software. So for example, if you're trying to run a certain app, you package up a container to have that app and all its dependencies, this bin libraries box here, just like with a virtual machine. But sometimes it's hard to figure out what are all the dependencies and what are the features of the operating system that we want to run this in that need to be included as well and made available. Sometimes it's easiest not to try and find out what all the dependencies are, but just dump almost or the entire operating system into the container, which is easier and faster than having to dig through and figure out which parts of an OS are needed to be in the container, which aren't. You might just dump the whole thing in the container to keep it simple. Now, that is fine, but it goes against a little bit the mantra and the advantage of a container if you were to do that. However, there are very lightweight operating systems that are really developed for this purpose, or at least to a large degree to assist in this purpose. So for example, Alpine Linux is an extremely lightweight version of Linux that doesn't have any of the fluff that other Linux operating systems might have. And so it's very easy just to say, okay, we're just going to dump the entire Alpine Linux into this container. It's a very small amount of file space that we need. And then we don't have to figure out what are all the specific dependencies for the application we're making. We have the whole operating system in there. So it saves us time and effort. And still we don't have a large footprint because this happens to be a very small footprint operating system. So that's actually how many containers do it in practice, when in theory, they don't have to have the operating system or much of it, and sometimes at all, any of it, in the container itself. We've got two big players in the world of container technology. We've got Docker and Kubernetes. Docker is the container engine company. They make the container engine that almost everybody uses. And Kubernetes is an organization that creates the container orchestrator that is most popular. What is a container orchestrator? A container orchestrator is a tool to help you manage a situation where you have many containers running at the same time, or a situation where you want to have programmable logic to determine when to create a container, when to destroy that container. So for example, you're running some kind of an application, you're expecting to have 100 users, suddenly you have 1 million. You need to scale up quickly. Well, Kubernetes can be used to be programmed to say, well, if a certain amount of load is occurring, if you have a certain amount of usage of your container, spawn more of them. So you can easily program logic to manage, maintain instructions for when to create, when to destroy containers, and how to sort of program the interactions in a dynamic environment. So that's what an orchestrator would do. We would use the Docker container engine as our fundamental core technology for the containers, but the orchestrator would be there to help us manage and orchestrate many containers or the stopping and starting of containers in dynamic environments.